So let's get it started. Hello, everyone. My name is Zamani. Thanks for joining the CIIR Talk Series. It's my pleasure to host Dr. Benjamin Piwowarski. He was too kind to make his vacation a bit shorter to give us this presentation. I know Ben for years. He has been a very active member of the information retrieval and natural language processing communities. I think the first time I met Ben in person was in Paris when where he was the general chair of CIIR. We were just talking about it. That was extremely hot, one of the hottest days of Paris in the last century or something like that. It was impossible to walk outside, and we were spending all day either at the conference or at the museums afterwards, just to be cool. Benjamin has been working on various aspects of newer models for information retrieval, especially efficient models. He has been working on quantum physics inspired models for information access. He's been working on web search at Yahoo for a while. And now he's a senior researcher at the French National Center for Scientific Research, or CNRS, in France. Today, we are going to hear about closing the efficiency effectiveness gap with cross-encoders. And without further ado, please join me to welcome Benjamin. UMass is kind of virtual.
Yeah.
Please.
Thanks, Hamed, for the introduction, and hello, everybody. So what I will present today is basically two works we submitted in CIIR. Both were rejected, but anyways, we'll present them nevertheless, because I find it's an interesting topic. So it's the work was conducted by Matthias Bast and Victor Moran, two PhD students who I am supervising, and there was other co-authors that participated in the effort too. So basically, the basic outline of this talk lies in the fact that, well, of course, there are many different brands of neural IR rankers nowadays. But when you look at the effectiveness side of this of the spectrum, you have basically two kinds of models that compete, which are the cross-encoders. You have different brands, whether it's a decoder only or encoders only. The debate is still open, I think, which are effective but slow. And then you have late interaction models like BERT, which are faster, but which are less effective. There have been some work, I will talk and discuss them a bit later, trying to find better cross-encoders, more efficient cross-encoders, but still it's something that has not been worked on quite a lot. I mean, there have been a few papers, but not so much. And I think it's interesting because it's really, I mean, the ideal neural IR system would be a cross-encoder, at cross-encoder effectiveness, but with something which is at least as efficient as BERT, or maybe faster. So that's the intent that we had at the beginning of the work, was to reduce the cross-encoder as much as possible, so as to be as close as possible to BERT. We didn't succeed in this, but we got a bit a step further. So what I will present today is divided in two parts, and there will be an interlude around the experimental framework we are developing. So the first part is trying to look at the recipes that are train cross-encoders. And when we started to work on mice, which is the name of the lightweight cross-encoder we propose, there was no real study on what are the factors which are important to train properly cross-encoders. So we did an effort to try to compare 9 different backbones, 6 different training objective losses, giving rise to 162 controlled runs in the paper, reproducing and comparing distillation techniques for cross-encoders. And then the second part of the talk, after the interlude, we'll discuss the effort we had towards stripping down a cross-encoder and giving rise to mice for minimal interaction cross-encoders for efficient rerun. So yeah, feel free to interrupt me at any point, especially I cannot see you, just see Ahmed. So feel free to interrupt at any point if you have any question. So the two questions that I want to address somehow here are what are the best losses that we can design, and how to design cross-encoders that have as few interactions as possible so that they can be fast. So let's start with the reproducibility study we did. So as I was saying, I won't go through the list. I guess most of you know at least some of them, or at least ModernBERT baselines, which was conducted done in 2019. There are many different works trying to show different ways to train cross-encoders. So you can vary the backbone, you can vary the loss, it can be pointwise, pairwise, listwise, or contrastive. It can be distillation. The distillation can come from other cross-encoders, it can come from LLMs, as more recent works have proposed. And as I said at the beginning, there are no really there is no study that tried to look at the different losses and backbones and try to see which works and which don't. So what we did is basically to do an experimental study. The choices we made was to hold constant a few things. So the things that we maintain constant within the experiment is that we use the State V3 distilled BERT first stage ranker, where we took the top 1,000 first documents. We use MS Marco V1 to train the models, then with different data sets. So when it comes to distillation, we kept the same tokenization, or we kept the tokenization of the backbone. We kept an identical sequence length, and all the evaluation suite was kept constant. The hyperparameters were like the learning rate and batch size were determined just once, basically for each backbone. And we also did some, we did try to look at the variability of the training by running 3 different training and to have an idea of the variance of the results. As I said, we varied also the backbone. So we trained 9 different backbones from 17 million parameters to 184 with 6 different training objectives I will expose a bit later. So that gives rise to 162 training runs. With respect to the backbones, we'll go fastly. We used, of course, BERT and then Roberta, Electra, because all the models were selected because they were already used in previous cross-encoders works. And Electra because it was trained a bit differently than the others with classification loss. We use also MiniLM V2 because it's a very lightweight backbone. And then we use more modern architectures like ModernBERT, which was interesting also because we could vary the number of parameters of the backbone from 17 million to 150. And we also experimented with DiBerta V3, but I won't expose the results because there was some bugs actually in the training. And the experiments are running again. We will include the results in the V2 of the paper. With respect to the losses we use, so all the losses are quite classical. We use the pointwise loss, which is the binary cross entropy loss, which was used in ModernBERT. We also use a few pairwise losses, like the hinge loss that was used in CIIR. the same year as BERT. We use listwise or contrastive loss like InfoNC, which is pretty standard nowadays. For this one, this is something that we are trying also to change the current experiment we are running. We used a set of negatives which was different than the one used for BCE and Hinge. That is, we use Colbert V2 hard negatives, which might provide a better signal for the cross-encoder, and where we used 8 passages per query in the info and CE loss. Then to continue the list, we used another pairwise loss, but this time in a distillation mode. So we used the margin MSE, which was proposed by Hofstetter in 2020, where we use the Hofstetter, BERT, CAT, and several teacher scores to train the models. It was the same that were used, for example, to train Play V2. And then we used 2 distillation driven by LLMs, which were proposed recently in a work by Schlatt in CIIR 2025. The distilled rank net loss, I think it was not proposed in this work, but it was in another work, but it was also compared in the Schlatt work. And the ADR MSC loss, which is listwise loss driven by an LLM. Okay, so while all those losses give us quite a good range of the losses that were used to train cross-encoders so far for the RLIR systems. For validation, that was a tricky part. We started initially with validating on MS Marco, standard dev set, small fraction of the dev set used for this. And then after discussing quite a lot with remember the name, the one from SentenceBERT, back in my mind, sorry for this. We ended up validating not on just in-domain data, but also a little bit of out-of-domain, and we used a mix of BERT and of MS Marco validation, the datasets to validate the results and to select the best the best checkpoint for each run during the best checkpoint during the training. With respect to the test set, so we used 3 different ones: the in-domain with MS Marco Dev and track DL19 and 20. We use BR13. So in this case, we cannot say it's out of domain anymore, but you have to be aware that most of the good baseline, cross-encoder baseline are in the same case, actually. I mean, the one on sentence transformer have been trained with validation on another BR, so they cannot be considered as fully out of domain. But it's close by, but not exactly. And then because of that, we also selected out-of-domain dataset like the load search one and track robust 04. And as I said, we use 3 runs per configuration to have a look at the variability of the results. Okay, so now let's go to the results. Yeah, this slide is just to say that first, we reproduced some recipes from the literature and just to check that everything was okay, and we did to some extent. For example, distilled rank net was on DL19 was very close to what was reported, and then for DL20 it was a bit further away, but not that much. Okay, so that's the big picture of the result. We'll go into details a bit in the next slide. So here you have the results basically for all the losses for all the models. They are ordered by number of parameters. And then for the 3 dataset in domain, MS Marco, near out of domain with BER, and then out of domain with LOT and robust. And each time we use just one metric, which is NDCG at 10, so we could average them, even though robust or 4 is NDCG is not the standard metric for us. So the first thing that you can notice is that for small model sizes like 1817 and 1832, we had a lot of variability when it comes to some metrics. So for example, BCE, distilled rank net, and ADR MSE were very unstable during training and gave rise to bad results. Then the second thing that we can notice is that mostly, apart from BCE, the losses are mostly equivalent in terms of performance when it comes to generalization. I will go into details in the next slide, so don't worry. To go a bit deeper in the results, first I will describe very shortly what we use to compare the models and how we perform statistical tests. So basically, what we did is to use the paired Friedman-Nemani test, which comes from a paper from Demshar in 2006. And he has an issue which is very comparable to what we have in machine learning in general and IR problems in particular, which is that the statistical test for comparison of more algorithm on multiple data sets, which is even more essential to typical machine learning studies, has been all but ignored. And so it's exactly the case we have. We have different systems we want to compare. We have different data sets. So just in a few words, what the test does is the Friedman part is just to check whether the differences are significant or not globally. What we do is basically to order the systems. So we order them for two different things. We either order the loss, keeping fixed the backbone and the data set, or we order the backbone, keeping fixed the loss and the data set. And then if all the losses or all the backbones are equivalent, you will have something where they will be ranked randomly. And so the null condition, where there is no difference between system, is that all the conditions, all the systems are as good. And this is roughly Chi2 test on ranks. And then if the test fails, that is when we have a statistical difference, we can use the Friedman test, which is based on the notion of critical distance in ranks, to check whether two losses or two backbones are different. So what I will use in this slide is the nearly equal sign to say that it's not significantly different on the Nemani test, the post-hoc. I mean, all the tests were significant, meaning that there was a difference. So we performed the post-hoc test in all the cases. So first result is that basically the best losses that we had are info NCE and margin MSE, with a slight advantage to info NCE. The second set of losses that were a bit less performing than the two info NCE and margin MSE was distilled rank net, ADR MSE, and the hinge loss, which were ranked around between rank 3 and 4 each time. And then the last loss was the BC loss, which was significantly worse than all the others. And you could see this in the first slide I presented. So basically, it was a bit unexpected. That was not what we expected to find. We thought at the beginning that the LLM distill losses would be better, but actually they are not better than info NCE or a margin info NCE, which is kind of interesting because info NCE just relies on hard negatives from Colbert in that case, and there is no distillation, so it's quite a natural results. And then that pairwise and listwise losses were better than the pointwise baseline consistently, which is a bit less surprising, but it was quite consistent. With respect to the backbone, so as I said, we exclude the beta from the results. We had, well, let me show them all at once. We have 3 different tiers. The first one was made of Electra, BERT base, and the big Ettin model and mini LM. So quite a good range of models in terms of number of parameters. And then Roberta and Ettin, 68 million, and then the 2 Ettins, 32 and 17 million. So, which is an interesting result because it shows that mini LM L12, sorry, is quite a good model when it comes to performance, and it's a very good choice because it's quite lightweight. We did run also. We did look at scaling low on the 18 suite. I would go fastly over those because they are not so surprising. I mean, it does improve with scale, of course. Then there is no clear cut in terms of which loss is the best, as you can see between the influency in circles and margin MSE in squares. It depends on the scale of the model, mostly. And the last result is that it saturates. So I mean, going beyond the 150 million parameters is not really needed, at least with our experimental conditions. Okay, so yeah, I will conclude on saying that we are updating them. So, but we release on Hugging Face all the cross-encoders that were not all the cross-encoders, part of the cross-encoders that were trained, at least those that were the most performant. And then we release everything on GitHub when it comes to the code and the evaluation code. There are some caveats, of course, that like in any paper that I want to underline. The hyperparameters were just tuned once based on the size of the backbone of one backbone of this category, which might not be optimal. We did use a single teacher ensemble and a single first stage, although I don't think it has a big impact on the results. We used negative sampling that was the same with the Schlatt LLM distillation. And we didn't try to look at the different LLM teacher that was available. Okay, so there are no questions on this, or maybe we can wait until the end of the talk. It might be simpler. I will just do a quick interlude on the XPMIR stack that we used to perform all the assay experiments. So, well, it's something that I worked on for years, and now it's my PhD student and Claude that do the work basically on this. The problem is that, well, as you all know, in information retrieval and machine learning, it's quite difficult to keep track of all the experiments you're running and all the pre-processing and all the which means dealing with a lot of folders, a lot of experimental conditions, and when you have to run one more thing, then it gets a bit more ugly, especially when you're near a deadline or you're during a rebuttal and you have to do new things quickly without messing everything up. So basically, that's something that the framework tries to deal with. So there are different parts on this stack. The first one is the experimaestro, which is basically an experimental framework, which is completely agnostic of whatever you use. It's basically based on configuration and task objects that are used to, I mean, the configuration objects are are there to configure. I will give some example, the experiment to give your experimental parameters, and then tasks are there to run some part of the processing. What distinguishes this framework from many others is that the graph of tasks is constructed from an experimental file, which is basically a Python code where you say how you want the different tasks to be changed, and how one output uses is used as an input for another task. It has some abstraction of where you run your experiments. You can switch from local to a Slurm cluster with the same code. And more importantly, if you run 2 times the same experiments, it will run exactly the same thing if you took care, of course, of the seeds and things like this. But its purpose is to be deterministic when you run the experiments. And it won't run the things which are already run. So you can add new things and new part of the experimental plan, and just run what's new. That's a screenshot of the interface where you can see different tasks running with their identifiers, which are computed automatically from the experimental parameters, and then tags which are helpful to follow what are the experimental parameters you are varying during your experiments. It just some indication of on what you're doing. And the interface allows you to look at the logs when the jobs are running on a Slurm cluster, for example, and the next thing in the stack is DataMaestro and DataMaestro IR, which are basically something which is agnostic of the field, and something which is less agnostic, which is done for IR. So it's basically something which is a bit more generic than IR datasets at the beginning for the DataMaestro part, but which purpose is the same. I mean, it's a way to give you it's a tool that gives you an abstraction of what is a dataset. A dataset is basically an ID, and then a way to download the data if it's available, and then an API in Python. And then for the IR part, you have all that standard things like MS Marco, track, deep learning, BERT, loads at the moment. There are also the distillation datasets, which are used to train the cross-encoders. And an advantage compared to IR datasets is that it has a kind of a good API where it's easy, for example, to support conversational search, which might not be easy with the structure in IR datasets. And then finally, experimaestro, go a bit faster on this, is something which uses experimaestro and DataMaestro IR, and it implements a lot of the components which are useful for conducting your IR experiments, and all the experiments in the cross-encoder study and in mice have been conducted using this library. So I will just give you some example of what can be done with this library. So this is an example of the loss selection in the cross-encoder paper, where we basically say that depending on the loss name, type of loss, we use either a distillation pairwise trainer or a distillation listwise trainer, which are 2 different ways to train your IR system. And then you have parameters which are other configuration or values like the batch size, for example, that can be used to parameterize your experiment. And each configuration object can be composed with the others. This is how cross-encoder is learned at the end. So we have the cross-corer, which is basically your cross-encoder, with the tagging system that allows you to track down the experimental parameters you want to look at. And then you have the main learner object that is submitted. This is the task is sent to the Slurm cluster or locally or queued locally to be run. Okay, I will just skip this. So yeah, I guess the main feature of the framework is to cache the intermediate artifacts, so you can reuse them for other experimental parts. You don't have to do any folder name guessing, no manual bookkeeping of which run correspond to which configuration. This is all tracked down, and it can run locally or with Slurm. It can show you tensor words through SSH or not, and many other things. But it begins to be quite stable at the moment. Okay. Now to the last part of the talk on the mice project that we had. So, well, we'll go fastly also over there, over this, because you know this. The ranking pipelines are usually two-stage. You have the first stage, which is fast, and then you have the re-ranker phase as the cross-encoder, which has to be accurate. So in this work, we focused on the re-ranker. We used also a splayed V3 model as our first stage, and our goal was to look at how to make cross-encoder faster and more efficient. So this was already discussed. So as you know, you have lots of different cross-encoders. This slide is more interesting. It's more related to the landscape in terms of efficiency of cross-encoders. So to make cross-encoders faster, you have different ways to do so. You can use smaller backbones like DistilBERT or MiniLM. That's the first easy way to stream down the efficiency cost of an information retrieval engine. You can also do things which are more frequent in BERT because it has an impact on the index size, but which is also interesting when dealing with cross-encoders, is to reduce the number of interaction tokens, which was proposed in re-ranking with compressed document representation recently. You have another way, which is the one which interests us the most, which is basically to have to have less interaction in your cross-encoders. And I will detail the works afterwards, so we'll skip this part for now. And the last kind of things that you can do is to try to early exit, that is to stop computing the relevance information, usually the CLS token representation, as soon as you have some evidence that won't be needed. So you have different ways to do this. There was an interesting work in CIIR or CIIR last year, sorry. Beginning to be tired around this. Okay, so let's go into the mice proposal. First paper, we looked at the losses, and in this paper, we looked at first at which computation are necessary at all. And the starting hypothesis, which was backed up by a lot of related works, is that most of the cross-encoder interaction are superfluous. So when we look into this hypothesis for the different papers which strongly hint to this, or that show, well, more than strongly hint that show this, are the following. So you have Deformer, which was more in QA, and PreTTR, which was done by McAvney and co-authors in 2020. So shortly after BERT, ModernBERT was proposed. The basic idea is depicted on the bottom left of the slide. So this is PreTTR, where basically what they did is to mask the attention between the query and the document, or the document with the query, during the first L layers of the cross-encoder. Then PreTTR was a bit different to what we did, because what they did is to compress the vectors, going, I think, from a dimension of 768 to 128, so it can be stored on disk. And then at query time, we just need to run the cross-encoder from the layer L+1. So there is a decompression phase that decompresses the vectors from disk so you get the different token representation. And then you let the interaction between the query and the document happen, so you can compute a final score. So in this work, they've shown that they could gain a 42 time fold latency with a bit of effectiveness loss, but not that. Same year, different conference, and it's a bit closer to the mice work. Actually, we didn't spot this one when we were working on mice, but its spirit is its architecture is very close to what we did. What they do is to go a bit further than pre-TTR. Actually, there is no compression phase. You represent the document and the query separately. So using two distinct encoders, actually, with distinct parameters. And then you have a given number of interaction layers where you alternate between self-attention for the query and cross-attention for the document. There was another work, but I will skip it because it's more a bioencoder, but it's also based on this idea of pre-encoding things. But in all the cases, and the basic idea is that we can pre-encode the document, and this can be stored somehow, and this can be used at query. More recently, there was a paper by Schlatt. So they didn't exactly look in the same direction, but they did look at similar techniques. What they did is, and the problem they had was to deal with long documents. And what they did is basically to use windowed self-attention for the document token. This is the green diagonal you can see on the graph on the left-hand side. And they masked all the attention between flowing from the document to the query. So the query tokens would attend to the document tokens, but not vice versa, and which was something a bit surprising, but I will discuss this. Next slide. Okay, so now, yeah. This, yeah. Just to motivate this a bit further, we did work on interpretability things with Matthias Bast. And throughout the previous interpretability work and the work we conducted, everything suggests that there is an information flow that goes from document tokens from document tokens to query tokens, and then from the query tokens to the CLS, which are directional attention processes and not bidirectional as was used in most models. In the work that we did, which is under review at TOIS with Matthias, we've shown that cross-encoders follow roughly a 4-stage pipeline. So you have first contextualization phase, where each layer, the transformer self-contextualizes the query and the document independently. Then there is a lexical matching phase, which is in the early to mid layers that detect exact matches between the same tokens. And then there is a semantic phase, semantic matching, which happens in the mid to late layers, and which match contextualized neighbors. And then the aggregation finally that pulls the relevance from the query tokens representation into the CLS. Sorry. To maybe. Sorry, I'm trying to find the slides I wanted to show you, which disappeared. It's not there anymore. So I would just summarize what we did in the first part of the paper, which was, yeah, we did a few things. The first thing was to look at what happens if we mask some of the direction in a cross-encoder. And we've seen that for mini-LM, we could mask a lot of attention without retraining the model, and the model would still perform quite well. Then we did retrain using some specific masks so that we could mask some attention between different components. So the different components are the CLS, the query tokens, the two SEP tokens, and the document tokens. And showing that, well, when you increase masking in the model, yeah, I don't have the figure anyways, you had, well, you could do, I mean, you could attain the same performance as the original cross-encoders. And even for some masks, it could exceed the baseline, showing that the current architectures, I mean, a full cross-encoder architecture might be harmful if you don't train it properly. We did a few other things. The first thing that we did is to try to see what was the right moment to cut the model. So going back to CIIR, for instance, there is the self-contextualization goes of document and queries separately goes up to a given layer. So we looked at this, and we found that basically for mini-LM, it's around the fourth layer that the drop occurs. For 18, which is 17 millions, it's around the third, and for 1832 millions, it's around the sixth layer that we obtain the last best performance before the drop. If the interaction, meaning that if the interaction starts too late, then the transformer model cannot recover from not having interaction at the first place, and we suspect this is because of the exact matching process. As the tokens are contextualized, then there is a moment where the model cannot recover exact matching. So the mice architecture we proposed is quite close to the work of Carol and Kellen that I presented earlier. The main difference is the number of interaction layers that we had at the end, and the way we perform the self-attention and cross-attention, which is inversed with respect to this model. And we also performed a lot of experiments with different backbones and different layers. And the final things that we did compared to the work I presented is also that we noticed that some of the conclusions didn't hold. In particular, what they did is to cut the model in two and to have non-interaction phase and then followed by an interaction phase, unidirectional or interaction phase, and this not work properly, as shown. This does not work. Properly. So the just to describe the last bit of experiment that we did look also at how many interaction layers to preserve in the model. That's what's displayed in this figure. So we basically cut a mini-LM, for example, at layer 4. So having two separate encodings before letting the cross-encoder, the query and the document interact. Basically, the query looking at the document tokens, and we had a clear signal that 3 interaction layers were the best. Before, it doesn't work as well, and after, the performance is just exactly the same. So you don't gain much at having more interaction layers. Then we perform an experiment. So it's just an extract of the table of the paper, where we compared different versions of mice based on mini-LM or on different 18 models. And well, the main conclusion is that we can, for example, for the mini-LM version, preserve much of the performance. For example, we go from 63.8 in NDCG in domain to 62.2. But at the same time, we gain a few points in out of domain. We go from 44.7 to 50.5. And so overall, it's quite comparable models with different properties. And the out of domain gain was interesting because we noticed that it was mainly due to a few subsets of data sets on which BM25 was performing well and not the cross-encoders, which means that well, this kind of training and this kind of architecture was kind of very useful in gaining exact matching. Sorry, it's been a long week. Be a bit tired. Yep. The last experiment we did also was to look at the latency issues, and well, this is a table, so it compares things which are not directly comparable because CoreBERT is the standard CoreBERT, and mice is mini-LM. But the rationale of this table is that performance-wise, it performs as well. And in terms of latency, we can gain quite a lot because we can be quite comparable to a CoreBERT model with a good speed up if we pre-compute the document tokens beforehand. So it's really an alternative, we think, to CoreBERT. Especially if we can try to push a bit more the architecture, and we think we can gain a few points or parts of points again, and just relying on, for example, splayed models, which can be used for cheap first stage ranking in case of BM25, or the played models used for CoreBERT, for example. I will skip this one. This one also, I will send you the slides anyway, so you can look at this. I will end with this slide, just showing the two things I presented today: the effort on reproducing cross-encoders that we are continuing at the moment to try to cover more ground, and the mice architecture that we are also improving at the moment to get even better in terms of the efficiency effectiveness trade-off. Well, thanks a lot for your attention, and we'll leave a bit of time for questions. So don't hesitate if you have any question. I know that I have been unclear in some parts because I tried to skip some of the slides. So yeah.
Thank you so much. So I think there's a question in the chat from Harshan. Harshan, would you like to unmute and ask, or would you like me to read the question?
Oh, sure. I can ask it. So, thanks for the great talk. So I have a question about the first part. So, I think BC loss is quite popular. I think sentence transformer using that as a default. So do you have some intuition why like this popular loss does not perform that well in your experiments?
I think, it was quite consistent because it was really a clear signal. It was whatever the architecture and whatever the backbone, and almost whatever the negatives. We are currently running further experiments because one of the reviewers pointed out that we didn't use the same negative. So if I go back to the slide, to this slide, I think, yep. Basically, we switch from the official triples that are used basically from BM25 negatives to CoreBERT V2 hard negatives in the influency loss, and I think this was one part of the issue. the thing is that hinge loss is also performing better than BC. So at the end of the day, I think that basically it doesn't provide a good enough signal for training. I don't have a clear view on why, but what I can tell is that all the other losses like influency or the distillation wise have a much better signal, because influency is leveraging a set of negatives, and we know that in contrastive learning, providing more negatives is something which is important. And the distillation provides, is obviously solving a lot of problems that we have in IR, which are related to the problem of the false negative, which are a lot present in MS Mark. And I think that BCE compared to hinge loss, to finish the comparison, is much more sensitive to this kind of negatives. Because if you predict a document to be relevant where it's noted as being falsely non-relevant, the BC loss provides a strong push in the opposite direction when the cross-encoders are non-saturated. I guess it has a very detrimental effect on cross-encoders, especially.
Got you. Thank you.
Okay. So feel free to unmute yourself and ask question. So Hamed had to leave for teaching, but he sent me two questions to ask you. I think you responded one after he left, but I read it. So one is about like how does the efficient cross-encoders you presented perform compared to models like Colbert that are biencoders, more similar to biencoders, which I think like we had a comparison in the tables. So I move on to his second question, that is, how does it compare with hypencoder that construct query-specific similarity functions for computing relevance for each document?
Sorry, can you repeat the question?
Yeah, I also copy that in the chat, if that helps. So it says, how does mice, I think, compare with hypencoder that construct query-net, which is query-specific similarity functions for computing relevance for each document?
Yeah, it's a good question. We didn't think at all to look at how to compare to this kind of models, because it's I didn't think of. I mean, it's a quite different architecture, the hyperencoder architecture, and our intent was really to look into streaming down the cross encoder as much as we could, and to remove as much as of the interaction as we could, with the idea that maybe we could get into Colbert ground, where you can, for example, retrieve document vectors which are clusters which are close to the query tokens, because the self-attention, the cross-attention mechanism that we use in mice is doing basically this. I mean, it replaces the maxim with softmax, and with several layers. And we thought it could be, I mean, we could approximate the process and have something which is more progressive, whereas the hyperencoder, which is the query to compute a network to compute the relevance of a document, might not be that. I mean, I don't know. Might not be that easy to have this kind of direction. because the computation function that gives you the rise to the network is not that obvious to analyze. So I think it would be one of the difference. But I agree that the models in Spirit are going into the same direction.
Yeah, cool. Thank you. So in the table of results, I think I saw that like in domain performance was not directly correlating with out of domain. So like
In which one?
In the table of results, like comparing, yeah, this one. So there's something that like from mini LM baseline to mice, like in domain performance drops a little bit, but out of domain performance increases a lot. Is it possible that there's some sort of overfitting when we're training like the mini LM, like all parameters, like we have full interaction? I mean, like, yeah.
Yeah, I think it would be rather the opposite of overfitting. I think we interpret it actually in an opposite direction, which is that it kind of underfits the MS Marco dataset, the in domain, because I mean there were two things that first because of the out of domain performance that increases. So usually it's a sign that the model generalizes better at the cost of being a bit worse on in domain data. So that's
Right.
the first sign.
Yeah.
And the
So
second is
oh, sorry.
And the second is when we looked at the results and we noticed that actually the data set on which the mice model were working better was those on which the cross-encoder performance was the worst compared to BM25. So basically, we interpreted those as when exact match is more needed than usual. So it seems that that kind of architecture is more sensitive to exact matching than a full cross-encoder that integrates more maybe semantic signals.
I think I missed the last part, but like if we like the baseline mini LM, if we train it for less steps, is it possible that or like fewer amount of data, is it possible that we see greater out of domain performance or not?
I'm not sure. I wouldn't bet on it because actually it's a bit related to the experiment we did. Yeah, on this one. So I dropped the slide where the masks were depicted visually, but basically the mask one, mask 0 is basically no masking in self-attention, and mask 1 was masking very obvious things that we don't want to have, which is basically attention between the SEP and I don't remember exactly, but between the SEP and the query tokens and things which we were thinking was not really helpful. And it did improve a lot the out of domain performance. And then with the mask 2, it was which was a bit more aggressive. It was the out of domain performance was stable, comparable to mask 1. So the conclusion of this is we think that basically because of the architectural changes we are making with masking or with mice, we help this kind of out of domain generalization, but the model has less opportunity to overfit the MS Marco dataset.
Yeah, cool.
Yeah.
Yeah. So I think we're out of time. I just asked a very quick last question. So there's a new trend of like this cross-encoder re-ranking that do reason first and then predict the relevance. So I think that was not part of the study, but do you think like masking like cross attention in those all like this masking also generalized to those type of re-rankers?
I don't know. I mean, it's something that could be. That's something that could be attempted. I have no answer to this, actually. I think I mean, to start answering the question, starting again with some very simple experiments like masking some part of the attention, for example, just having the attention flow from the thinking process or thinking tokens to the final decision could help to see whether the model could rely just on the reasoning part, with quotes, like this. But I don't know. I mean, but it would be very much targeting an interpretability of the model rather than trying to make it more efficient as we did. I mean, the target of the masking and the interpretability studies that we did was really targeting the question of how can we remove as much as possible of the model without changing performance.
Right.
But
Yeah.
yeah.
Yeah. Thank you so much again for giving this interesting talk and for like staying late and giving the talk. Yeah. Thank you.
Yeah, thanks, Negin. Well, thanks to all. I don't see you, but
Then-
bye.
Bye. Thank you.
Bye.